In this video, we're going to talk about implicit differentiation. I've got a lot of information up on the board here. I want to start with this left-hand side. Here we're going to be reviewing implicit differentiation as we learned it in first semester calculus. So here I've got the equation for the unit circle, and probably when you encountered that in first semester calculus, you just said, oh, that is the unit circle. You probably didn't think of that as a level curve for this function, f of xy equaling x squared plus y squared, but it really is. It's the level curve, f of xy equals 1. Okay. So when I have an equation in two variables, as long as I put all the variables on one side, I can think of that equation as just describing a level curve for a function of two variables. Now that curve is going to exist in two space, and it may or may not be the graph of a function. Here, this is not the graph of a function because it fails the vertical line test. But with the circle, there are two corresponding functions that I can get. If I try to solve for y, I don't get a unique value, but I could get y is the square root of 1 minus x squared. That would give me the function corresponding to the top half of the circle. Or I could solve for y and get y is the negative square root of 1 minus x squared, and that gives me the bottom half. So no one function gives me the entire circle, but there are these two functions. If I put their graphs together, I get the entire circle. And basically the information about those functions is encoded in this equation. So that if I wanted to find the slope of the tangent line at a point here or at a point here, I could do that without having to explicitly solve for y first. That's what implicit differentiation allows me to do. I essentially say that that y is some function of x. Okay. I actually know it's one of these two functions, okay, depending on what point on the circle I'm talking about, but I treat that as a function of x, and then I just take the derivative of both sides with respect to x. Okay? Now here, I've got the equation for the unit sphere. And again, when we first saw the unit sphere, we probably just thought of that as the equation for a sphere, because we were just learning about spheres. We hadn't yet talked about functions of more than one variable. But I can view that. That's a level surface for this function, g of x, y, z equals x squared plus y squared plus z squared. That's just the level surface, g of x, y, z is equal to 1. Okay. So anytime I have an equation in three variables, again, if I move all the variables over so that they're on the same side of the equation, I can view that as a level surface for a function of three variables. Just like with our level curve, when I look at the graph, it may or may not be the graph of a function. This is not the graph of a function because it fails the vertical line test. There are points on the xy plane that have 1 point above and 1 point below. That's not a unique output. But just like with the circle, there are two functions, one function that would give me the top half of the sphere, and one function that would give me the bottom half of the sphere. And I can find those just by solving for z. Of course, when I solve for z, I have to take plus or minus the square root of what I get. So the top half is z is the positive square root of 1 minus x squared minus y squared, and the bottom half is z is the negative square root of 1 minus x squared minus y squared. But again, if I wanted to find the partial derivatives for this function or this function, if I wanted to find the partial derivatives for a point on the sphere, it would not be necessary for me to solve explicitly for z in order to do that. I could use implicit differentiation. So let's take a look at how that works with this particular example. So if I have x squared plus y squared plus z squared equals 1. And let's say I want to find a formula for the partial of z with respect to x. Okay. So I'm saying z is implicitly a function of x and y. Now I know it's actually one of these two functions. In this case, I'm familiar with the graph. It's not too difficult to solve for z and get that I have one of these two formulas. But what's nice is I might have some formulas where it's very difficult to visualize the graph, very difficult to solve for the different options that z could be, and implicit differentiation allows me to find partial derivatives without that. Okay. So what I'm doing here is I'm saying, okay, x, that's my input variable or my independent variable. So that's the input. Z is implicitly a function of x and y. So it's not a formula that I have an explicit formula for, haven't solved for it. I just know it's going to be some function of x and y, and then I'm holding y constant. So x and y are my input variables, z is my output variable. That's usually how I think of things. Now, if I wanted to, I could say this equation implicitly defines y as a function of x and z. Then I'd be letting x and z be my input variables and y the output. I'm going to stick with the more conventional, think of z as the output, x and y as the inputs. So I'm keeping one of those as my variable, holding the other one constant. What's tricky here is now I have a third variable that I am thinking of as a function of x and y. So if I were to take the partial derivative with respect to x of both sides, let's warm up with the right-hand side. That's a nice confidence builder. That's a constant. Any derivative of a constant is going to be 0. Okay, now I've got 3 terms here, and they're all going to be different. If I'm taking the partial with respect to x of x squared, x is my variable. That's just my usual take the derivative, we get 2x. When I get to this term, y is a constant. The derivative of any constant is 0. When I get to this term, that's a function composition. That's this function z that I haven't bothered to find a formula for, squared. So I would use chain rule. I would say that's going to be 2 copies of z times the partial of z with respect to x. Now, I do need to use partial derivative notation. We do not use prime when we're talking partial derivatives. The prime notation is wonderful and lovely, but it means full derivative. There's no such thing as z prime in this particular case. So when we talked about the different notation that we had for partial derivatives, I could write z sub x to say the partial derivative with respect to x. I can write del z del x. I can't write z prime because then there's no way of indicating what the variable is, because z is implicitly a function of 2 variables. Okay, so this example is kind of nice because it separates out the 3 different types of things that we have. All right, and then if I wanted to solve for the partial of z with respect to x, I'm just going to move everything over. So I would have 2z partial x equals negative 2x. Divide both sides by 2z. Now, of course, that's going to be undefined if z is 0. Okay. Now, as long as that z stays in the denominator, I can see that that is undefined when z is 0, so I don't need to explicitly say that. But if I were to cancel it somehow, I'd need to explicitly say, hey, z is not allowed to be 0. This formula may or may not be valid if z is. This formula is definitely not valid if z is 0, and that just tells me that this partial derivative is going to be undefined at those places. Okay. Those 2's will cancel, and so I can say we just get the opposite of x over z. I think what's kind of interesting is if you take a look at what happens at the places where z is 0, that's going to be where we're on the xy plane. And we were taking a look at the partial derivative with respect to x. So we would have been looking in the plane where x is my variable, so we'd be holding y constant. So I'd be looking at these cross-sectional circles that I would be getting in a plane parallel to the yz plane. Notice where z is 0, vertical tangents. Derivative is undefined. So it's the algebra is consistent there with the geometry, which is kind of nice. Okay. So implicit differentiation works in this case. We're basically saying if I have a level curve for a function of 2 variables, I can use implicit differentiation same way we used in first semester calculus. If I have a level surface for a function of 3 variables, I can use implicit differentiation to say that z is implicitly some function of x and y. That's going to be true at most points on the curve. There may be some places where the partial derivatives are undefined, but that sort of falls out naturally from this process of finding it.